topic. And I know Tom already has discussed some of it, so I'm going to be quite quick introductory overview. So the idea here is that we want to extend Bayesian inference to the level of model. So here's the sketch of a useful way of thinking about this, perhaps. Level 1, what we have done so far, namely selecting implicitly or explicitly a model M and a prior for the parameters theta of that model. And given the model, we want to see what are the favorite values. Right? In a sense, we try to do regions for the parameters of that model, assuming that model is true. And to do that, we use Bayes' theorem here, which thus far we have used only constant. I might not. Oh, sorry. Thank you for pointing this out. Better? Sorry. So here, level 1, one model M with prior P of theta given M. And then what we've done so far is to use Bayesian inference to find the posterior distributions for the parameters of that model given the data up to normalization constant, really. We always have dropped the normalizing constant for the posterior for the purpose of inference, parameter inference. Level 2 is when you realize, well, actually, there are several possible models for your data. You want to know which one is best in some sense. What is the relative plausibility of each one of the models in the light of the data? And that's Bayesian model comparison. This is what I want to do next. And the key quantity here is the posterior odds. That's to say the ratio of the model probabilities after we've seen the data. If there are two models, there's just a ratio of model 0 to model 1 given the data. Level 3, if I have time, I will sketch quickly some ideas about model averaging, where you realize that none of the models on the table is clearly the best. You want to make inference on the parameters accounting for model uncertainty, accounting for the fact that you don't know which one of the models is the right one. So you might want to average over models by getting a model average parameter value, summing over posterior probabilities for models and the parameters for each one of the models. I call it level 3. Okay, so model comparison questions are ubiquitous in cosmology and astrophysics. Here are some examples. In cosmology, certainly, you might ask questions of the kind, is the universe flat? How star can evolve? Which inflationary model is best? And so on and so forth. Or in astrophysics, when you do exoplanets detection, as I'm sure we have discussed with Phil, we want to find whether the data support 1, 2, 3, 4, 5, 7 planets or no planets, etc. Dark matter and astroparticle physics, all of these questions where you always want to figure out whether there is an effect and whether a model with that effect built into it is better than a model with no effect. Those are model comparison questions, and they are best approached often using Bayesian model comparison. As Tom already said, so I'll go very quickly in this recap. Bayesian model comparison is based on this quantity here, the Bayesian evidence or model likelihood, that is the normalizing constant on the right-hand side of Bayes' theorem. And because it's the normalizing constant of Bayes' theorem, the evidence is given by the integral over the parameter space omega over the parameters of the model of the likelihood times the prior. Everywhere I've explicitly conditioned on M here to show explicitly that all of these things are conditional on a choice of model. If we're now interested, so the Bayesian evidence is the probability of the data given the model fully marginalizing out the parameters. That's why it's called the model likelihood, because it looks like a likelihood for the model itself. It's the probability of the data given the model. So now if you want the posterior probability for the model M, posterior probability is given again by using simply Bayes' theorem. So the posterior for M given the data is the probability of the data given the model, that's the evidence, times the prior for the model, divided by a normalizing constant, and now depends only on D. We have two models on the table, M0 and M1. The ratio of the posterior probabilities, this is posterior odds, the ratio of the base factor times the ratio of the odds of the priors. In other words, posterior odds, that's to say our posterior relative degree of credibility belief in the two models, is given by prior relative degree of belief in the two models times the base factor. These terms here, the ratio of the model evidences is called base factor and then denoted by B01. So in other words, if I tell you what the base factor is, you can then update your prior degree of belief in the two models in the light of the data to the posterior degree of belief. So the key to Bayesian model comparison then is the base factor between models. As Tom might already have mentioned, I want to stress that Bayesian model comparison, as the name implies, is a comparison between models. There's no absolute scale of goodness for models. James, among others, maintain that there is no point in rejecting a model like you do with p-values unless you have a better alternative. It's always a question of comparing model, never a question of asking, is this model good? Okay, again, a quick recap of what this Bayesian evidence is. It is effectively a built-in Occam's razor. It balances quality of fit versus extra model complexity by rewarding highly predictive models and penalizing parameter space. As I'm going to emphasize over and over again, the prior here is really important. In Bayesian inference, when you're doing parameter inference, the prior asymptotically disappears. We've seen that the posterior, for example, a Gaussian linear model, tends towards the likelihood for informative, highly constraining data, and the prior is forgotten eventually, asymptotically. Not so in Bayesian model comparison. The prior here quantifies the degree of wastefulness of the more complicated model because it gives you the plausible range of parameter values that the model predicts or effectively allows and controls the strength of the Occam's razor effect. And so the prior is even more important for Bayesian model comparison than it is for if. To see this, consider the simple one-dimensional example. Here we have a parameter theta with a prior in green and the likelihood in red. And theta hat denotes the maximum likelihood estimate for theta. We can compute the evidence for this model simply as the average of the likelihood under the prior, like this. And we're going to approximate it by saying that this is just the, if the scale of the likelihood is much smaller than the scale of the prior, then we can approximately compute this just by saying that this is the maximum likelihood value times the characteristic scale of the likelihood, delta theta, times the prior evaluated maximum likelihood point as an order of magnitude estimate. But because the prior is normalized, the prior height here at the maximum likelihood point is of order 1 over the width of the prior. So it's 1 over capital delta t. And so we get that the evidence is approximately given by expression here, where this term here is the maximum likelihood value. That means better fit, higher likelihood, higher evidence, as you would expect. Then there is a second term here, which is the ratio of the width of the likelihood to the width of the prior. And this term is typically smaller than 1. The likelihood is going to be sharper than the prior. And that term here quantifies Occam's factor effect. It penalizes models that have a wide prior for which capital delta theta is large. Therefore, there is a large wasted parameter space that the model allows, but that the data do not require. So it is in that sense, the model comparison favors the best model, the one that balances best quality of fit, this term here, versus extra model complexity, this term there. Okay, so finally, in terms of recap for Bayesian model comparison, before I move on to showing some examples of application, I want to look at the important case of nested models. Nested models are models in which you have one of the two models is a subset of the other. So there is one model that has got one or more extra parameters with respect to a baseline model, and many cases of interest are of this type. For example, whenever you ask, is there a signal above background, you're typically looking at Bayesian model comparison with nested models, where you have this background plus signal model reduces to the background only model if you set the signal to 0. So that's a case of nested models, and many other cases that we consider are of this type. That's why it's interesting to look at this example. So here I'm going to look at a minimal example where model 0 has no free parameter and predicts that the value of the parameter theta is 0. Here. Let me make this a little bit. Then there is a more complicated model where it predicts that theta is different from 0 with some prior p of theta. Here, in green. And the question is, do we need the extra complexity? Is the addition of one extra parameter describing, for example, a signal warranted by the data? So we can easily compute the base factor of the, given the comparison between these two models. I won't do it here because it's very simple, but I'll let you do it on your own. What you find is that the log of the base factor between model 0 and model 1 is approximately given by this expression. So here I have lambda is the distance of the maximum likelihood value, eta hat, to the value predicted under the simpler model, in this case 0, divided by the standard deviation of the likelihood, delta theta. So lambda, in other words, is the number of sigma significance of your extra parameter in frequentist terms. And so what you can see is that the log of the base factor is given by minus lambda squared over 2. Lambda squared is always positive, and so minus lambda squared over 2 is always negative. And that means that model 1 is preferred because log of B01 becomes negative, meaning that the odds are in favor of the more complicated model whenever lambda is large, whenever you have a many sigma detection for a parameter, what you would expect normally. Then there's this other term here, which is the log of the ratio of the width of the likelihood on the numerator, on the denominator to the width of the prior in the numerator. Because the prior is typically wider than the likelihood, this term here is always positive. This Occam's razor factor term is the one that prefers or pushes in favor of the simpler model. And so this term here is always positive, this term is always negative, and which one of the two models you prefer depends on the ratio of the two. And also notice from this that the width of the prior, delta theta, controls in an irreducible way the strength of the Occam's factor effect. So the wider the prior, the more wasted parameter space, the stronger the Occam razor, the stronger the preference for the simpler model will be for given data. While this is true, also notice that this is a fairly mild dependency. It's the log of the width enters, so it's effectively only the scale of the prior that's important, not the details of how it's distributed or how you distribute your prior mass. So, it's an order of magnitude dependency, so keep that in mind. It's important, but at the order of magnitude level. So finally, to conclude my review before launching into something else, this is my one-slide summary of Bayesian model comparison. So if you want to remember anything about Bayesian model comparison, if you remember this slide, I think that's great. So let me just spend a little time explaining the slide. So I've tried to depict this Bayesian model comparison for nested models in this two-dimensional space. Because this is Bayesian model comparison is always a two terms fight between quality of fit and Occam's razor. On the vertical axis, you see lambda, the number of sigma significance for your extra parameter, from 0 to 5 sigma. On the x-axis, you see what I've called the information gain. Information gain is effectively the Occam's factor, is the base 10 log of the width of the prior divided by the width of the likelihood. And if you express that in base 2 rather than base 10, you will get it in base. Okay, so the region here in black is where the information gain is negative. That means that the prior width is smaller than the likely width. So the posterior is prior dominated. In this case, arguably, you haven't learned anything from the data. Therefore, your model comparison really doesn't mean much. It's just a reflection of your prior. So let's look only at the region where the information gain is positive. So the color depicts the different outcome of the Bayesian model comparison comparing the simpler model where there is no extra parameter to the more complicated model where there is one extra parameter. In blue is the region where extra parameter is required with increasing levels of evidence. I'm going to come back in a minute on the Jeffrey scale. And so you can see, for example, you detect something at the 4 or 5 sigma level, according to the usual frequentist, likely-based confidence interval, then independently of what your prior is or what your information gain is, you always end up in Bayesian model comparison favoring this extra parameter. Of course, we all know that 4 or 5 sigma detections are very, very strong, typically. That's why we choose, or at least why the particle physicists choose a 5 sigma threshold before claiming discovery, because they know it's a conservative threshold. It's a very small p-value. And so Bayesian model comparison is consistent with that. It gives you the same result. But if you look down here at the 2 sigma level, the 2 sigma level is often a threshold that's conveniently chosen in astronomy and astrophysics to say that we've seen something interesting. At 2 sigma, we've seen deviations from this or that, or an anomaly, or a signal, or a source. At the 2 sigma level, you can see that actually there is not a shred of evidence in favor for the extra parameter from a Bayesian point of view. And in fact, if information gain is strong enough, if your occurrence factor effect is strong, at 2 sigma, you actually end up in this peak region, which is the region where the simpler model is preferred because of the Occam razor effect. And with any choice of prior, really, there is no way you can favor the more complicated model, even at odds of 3 to 1. And so the upshot of this graph is that you should remember that in Bayesian model comparison is always more conservative than the usual p-value hypothesis testing. And what constitutes in p-value sense a traditionally sufficient level of evidence for an effect, the 2 sigma level corresponding to a p-value of about 5%. In Bayesian point of view, on the Bayesian point of view, this is really very weak evidence. It's actually no evidence at all. If anything, it's evidence in favor of a simpler model, depending on your prior. To get anything of substantial strength in favor of the more complicated model, you need 3, 4, and above sigma. And there are good reasons for that. There are statistical reasons for it. I don't have the time today to go into why there's striking discrepancy between p-values and Bayesian model comparison. There's a fantastic article by Jim Berger and collaborators. Let me see if I can find the reference for you. I really recommend that you should read it. I can't find it, but I put it in the references. It really explains why that is. Okay. So this is my summary of Bayesian model comparison. Here's the Jeffrey scale. It's a scale that's been empirically calibrated. It's been traditionally, or it's become a usage thing to use it as a scale to calibrate different levels of evidence. This is just empirically calibrated. It doesn't have any basis except the fact that we feel that something that's got relative odds of less than 3 to 1 really is very undecided. Models are maximum 75 to 25% probability each. Not worth mentioning. And this is a scale that's logarithmic in the base factor, notice. So it's log B that's important. So the next threshold is 2.5 in log B, meaning relative odds of 12 to 1, or if it's two models, one of two models is 92.3% probable, max. And so that's weak evidence. Moderate evidence is up to log B of 5, and strong evidence is above 5. So that's a useful way of translating in the back of your mind strength of evidence in terms of quantitative values of the base factor, in terms of how to interpret. Okay, so a few examples of applications now. I got quite a few examples. I'll just try to give you a sense. I won't go into the physical details because that would take too much time, but I want to give you a sense for what this can be used for. So here's a classic example from a paper by Ferros and Hobson 2007, where we have a field in the sky. It's a noisy realization of an observation, perhaps in the optical. There's clearly a number of point sources here, and the question is how many there are. Here's these are simulated data, so we can take away the noise and look at the signal, and this is what the signal looks like. You can see from this picture that there are 8 sources here, but of course when you add instrumental noise, it's not so clear, and you kind of see where they are, but not really. So this whole problem is to compare models where you have 0, 1, 2, 3, 4, 5, n sources and decide which one is best. And so that's a problem that is best tackled using Bayesian comparison. Here you see the reconstruction that of the modes of this distribution. So this is a reconstruction done using the multi-nest nested sampling algorithm, more about which in a minute. But you can see that this reconstruction finds 7 out of the 8 sources, and these two sources have been lumped together in one single source, the black posterior mass here, simply because they're very weak and they're very close together. Look at the difference in log likelihood units from the brightest source to the faintest sources. So this axis here spans about 600 log likelihood units. So it's a huge dynamic range here that we're talking about. And then we can use the tool of Bayesian model comparison that I just sketched to compare situations where we have 1, 2, 3, 4, 5, etc. different sources, and stop when the evidence tells you that adding extra sources is not helping anymore, just fitting noise. Here's another example. This time you can't see what's going on by eye because those are interferometry observations of Sunyaev-Zel'dovich maps in the microwave background without going into details of the physics. Those again are simulated data where you have one case here where there's only background noise and 3-point radio sources which are polluting the image. Those are foregrounds effectively. And in the case on the right, you got the same situation, but there's a cluster at top, a galaxy cluster that modifies the spectrum of the CMB that you want to detect via this spectral distortion in the CMB. That's the Sunyaev-Zel'dovich effect. Now the question is, how do you determine whether or not there is a cluster, keeping in mind that the point radio sources are unknown. I mean, we know that there are in there, and we don't know how many of them there are, and we don't know whether the cluster is in there. So there's lots of complicated parameters that we need to infer and do model comparison as well. So in this example, you can see what you can do. You can compute the Bayes factor, the posterior odds for the two models. One is a model where you have a cluster, and one is a model where you don't have a cluster, but you might have point sources and other noise to determine. So in the case where there is no cluster in the map, you get that the ratio of the probability is 0.35. This is 3.1 in favor of the no cluster hypothesis. While in the case where there is a cluster, the ratio of the posterior probabilities is huge. It's 10 to the 33. So by using Bayesian model comparison, you can disentangle the presence of the cluster from the rest, while at the same time you also recover all the parameters of the cluster that you're interested in, such as the position, the temperature, the profile, etc. And so you can do both inference and model comparison in the same go. So those are two astronomical examples. Before I give you a couple of cosmological examples, let me spend a little time discussing numerical methods, practicalities. So what we need to do to compute Bayesian model comparison quantities is to compute the Bayesian evidence, this multidimensional integral over the parameter space, in order to compute the base factor. This is usually a multidimensional integral because omega, our parameter space, would be a high-dimensional parameter space, and computing integrals in many dimensions is typically difficult. Now, it can be done by brute force, by using Monte Carlo methods such as thermodynamic integration of population Monte Carlo, which have been used successfully in the past. The problem is those methods are typically very computationally demanding and expensive. It takes a large number of likelihood evaluations to converge to the integral. And you might not have the capability of doing that if the likelihood computation is expensive, especially. Then another method is to do what's called the Laplace approximation. Effectively, approximate the likelihood to second order around the maximum, which will give you a Gaussian approximation for the likelihood, and use a conjugate prior in the form of a Gaussian prior. Then we all know that the Gaussian prior times the Gaussian likelihood integrated over the parameters will give us an analytical integral that can be done very quickly. In fact, it takes no time at all. We know the solution. So this gives you a numerical approximation which can be poor and very inaccurate if your likelihood is strongly non-Gaussian, or it can be completely wrong if you have non-Gaussian tails or indeed multimodal distributions. Then there are two other methods I want to present more in detail. One is the Savage-Dickey density ratio, which is very useful for nested models. The other one is nested sampling, which I briefly mentioned before. Any questions so far? Okay, the Savage-Dickey density ratio then is an analytical expression that can be used in the case of nested models, which, as I mentioned before, is a relevant case because they happen quite often. So what we need is nested models. So M1 is a more complicated models which has got one set of extra parameters psi. And when you set those parameters to a certain value, let's say psi equals 0, then you recover a simple model and not. And a sufficient but not necessary assumption is that priors for the more complicated model are separable. In other words, the one prior for the probability of theta and psi under M1 is uncorrelated with the probability of theta under M0. So this is actually not a necessary condition. It's sufficient, so it's fine, but you can actually derive the Savage-Dickey density ratio with an even weaker condition on the priors. But it doesn't really matter, because in most of the cases, the reality is that the prior for the extra parameter is uncorrelated with everything else. So this condition is usually trivially satisfied. So under these two mild assumptions, then it's very simple. It takes just a few lines of algebra to show that the base factor between the simple and the more complicated model is given by this simple expression here. So on the numerator, you see the posterior probability density for the extra parameters marginalized over everything else under the more complicated model, evaluated at the value for which the extra model parameters psi reduced to the simpler model, in this case psi equals 0, divided by the prior for the extra parameters under the more complicated model at the same location. So graphically, if psi is a one-dimensional parameter, let's say that your more complicated model has got one extra parameter with respect to the simpler model, this is what it looks like. The base factor is given by the height of the one-dimensional marginal posterior for the extra parameter under model 1 at the value that reduces the more complicated value model to the simple model, divided by the value of the prior at that point. So it's the blue point, the blue value, divided by the green value. So this is great because if you've done MCMC to sample from the more complicated model parameter space and get the posterior density of the parameters under model 1, and you already have for free the marginal posterior under model 1 up to normalization constant. And if it's a one-dimensional posterior, then all you need to do is normalize it by quadrature, simple integral to do, provided that your posterior is close enough to this value here that you have good sampling of the tails. If you're far away in this direction, then it might be that your posterior density is not well sampled in the vicinity of this value here, in which case, arguably, you need the extra parameter because you are many, many standard deviations away. But, if you are, I found in numerical experimentation, and this works, standard methods work well about 2 to 3 sigma into the tails of the distribution for Gaussian distributions. If you're anywhere further away than that, you will need to look at more sophisticated sampling techniques to make sure that you get a good estimate of the height of the posterior far into the tail. For example, tempered Monte Carlo would be a good choice. But okay, let's say that you have this accurately enough, sampled accurately enough, then you have access to the standard thickness to ratio for free. So you can do Bayesian model comparison without having to worry about doing the multidimensional integrals that are characteristic of the Bayesian evidence. Also, looking at this expression here is useful because it clarifies the role of the prior. In other words, you can see here that if I change the prior, if I change the width of the prior specifically, if I make the prior wider, the height of the prior has to drop because the prior has to be normalized. And when the height of the prior drops, the Bayes factor increases, thus favoring the simpler model, as we said before. So you can perform a sensitivity analysis for your Bayesian model comparison result at the level of importance sampling, for example, or even just by analytically rescaling this result. You can use it to test the robustness of your different choices of prior, which is always something that I would recommend doing. And finally, this expression here, I want to emphasize, does not rely on Gaussianity of the likelihood or the posterior. This is valid in general, as long as insofar as you have a good sampling of the posterior. It doesn't matter even if the posterior is multimodal or unimodal or Gaussian or not. Insofar as you have it correctly normalized marginal density here, you'll be fine. So this is often a useful way of working with nested models. Now, what if the models are not nested? Then arguably, perhaps, one of the best tools that has emerged in the last 5 years to do this kind of integrals is nested sampling. And I don't know if nested sampling has been covered in detail so far in the school. I'll give you a quick introduction to it. Nested sampling is an algorithm originally devised by John Skilling in 2004. I believe I first heard about it, although the reference here says 2006. That might be because that paper is, I think, is a maximum entry conference proceeding that took a while to come out. And so the original idea of John was that we can recast the complicated multidimensional integral for the Bayesian evidence in a simple way by a suitable reparameterization of the problem. So let's look at it here. Here we have our integral for the Bayesian evidence. It's the integral of the multidimensional parameter space theta of the likelihood over the prior. And now let us define this quantity x of lambda. X of lambda denotes the fraction of the prior mass that sits above the iso-likelihood contour of level lambda. Okay? So in other words, if I have a parameter space, I look at where the value is lambda, then x of lambda is the fraction of the prior mass above that contour. With this definition, then it takes a moment of thought to realize that you can recast the integral here into one-dimensional integral integrating dx from 0 to 1 times L of x, where L of x is the inverse of that expression here. So what this does, it transforms a multidimensional integral into a one-dimensional integral over this function L of x, which maps the likelihood function as a function of the prior fraction enclosed within that likelihood level. Okay, I know this is a little bit intense or a little bit dense the first time you hear it. Here's a picture of what this does. Here's our two-dimensional parameter space, and what this transformation is doing is saying, okay, here is a iso likelihood level. And so if I know where this iso likelihood level is, I can compute what is the fraction of the prior inside that level. And that's going to be x equals something. And I know what is the value of the likelihood at that level, and that's L of x. The average likelihood under the prior average over all parameter space is going to be equal to the integral under this curve here, which is a one-dimensional integral from x from 1, which corresponds to the entire prior space, to 0, which corresponds to the peak of the likelihood. So if I can do this mapping, then I can do this one-dimensional integral easily, because that's a one-D integral that I can do with many methods. And then I'm done. Okay. And so the idea is then how to do this transformation numerically and how to do this mapping. And the idea is nested sampling. Here I'm going to show you a little movie where nested sampling works by throwing down a number of points, a number of live points, as they are called, randomly prior box, which is this square here. Then what you do, you evaluate the likelihood at each one of those points, and you pick the point that has got the lowest likelihood. And then you replace this point by another point which is drawn from inside that iso likelihood contour uniformly. So it's drawn from the prior uniformly under the constraint that it has to sit above the likelihood level of the point that you've just taken out. And then you loop. So by doing that, every time you take out one point, you're replacing it with a new point, which by construction sits at a higher level in the likelihood. So you nest from the outskirts of the likelihood towards the peak of the likelihood, but peeling away the layers of an onion. Let's see if I can make this movie work. So you can see that here, points of low likelihood are being replaced by points of higher likelihood. So the cloud of points is nesting from the outskirts towards the center and climbing up the likelihood mountain. As it does so, it maps out this curve here, which is here in logarithmic units, log of the likelihood as a function of log of the enclosed prior fraction. So if you have this curve here, then your Bayesian evidence is going to be the integral under the curve. So this is a very neat idea which has been implemented in a very efficient way by Ferretz and Opson in the so-called multi-nest algorithm, which uses an ellipsoidal decomposition to work out how to make this replacement. The hard part of nested sampling is to decide how to draw the next point. Because, of course, the next point has to be drawn above the iso likelihood contour, but you don't know where that contour is, because if you knew where the contour is, you wouldn't be doing the sampling in the first place. So that's the hard part, and the technical solution that they've come up with that I won't go into. Here's the reference of the paper. But let's just have a look at the performance of multinest in one example. Here's an example where we have Gaussian likelihoods. It's a Gaussian mixture model with 5 likelihoods, 5 Gaussian likelihoods. So it's Gaussian, but highly multimodal. The reason why this is a nice example is because for a Gaussian mixture model, you can compute the true evidence analytically, and this is the result. You can also compute the evidence by thermodynamic integration, and the result here is a good approximation to truth within the error bar. It's a fairly large amount of likelihood evaluations, about 10 to the 6 likelihood evaluations for this example. Multinest can achieve the same result, same accuracy, with 2 orders of magnitude less likelihood evaluations. So it's a much more efficient way of doing this integral, which also works for highly non-Gaussian likelihood. This example here, where the likelihood function is not only bimodal, but it's the shape of a hollow cylinder. It's like 2 chimneys, essentially. This is a very hard problem to sample from. If you try with any vanilla MCMC method, it will fail badly, I assure you, because it's just a very difficult problem to find a good proposal distribution for. You can see that the reconstruction by multinest is very good, and it finds the 2 modes without problem, and it's able to navigate the rim of this this likelihood in a very nice way. And so this is a good method, and the code is public. It's called multi-nest. You can download it and plug it into your problem of choice as a sampling. It will give you both a very good sampling of the parameter space for highly multimodal likelihoods and nasty degeneracies, and an evaluation of the Bayesian evidence that you need for model comparison. And what you can see here, the final thing I want to say is that the efficiency of multiness is very good, up to about 30 dimensions, where the efficiency is still about 8%. Above 30 dimensions, there are technical reasons why the method becomes very inefficient and your efficiency goes through the floor. So don't try to use multiness for a very, very high dimensional parameter space. I've seen there's a paper recently by Ferros and Skilling where they introduced something called Galilean Galilean nested sampling, which I've skimmed through the paper. I haven't studied it in detail. They claim it's good. It's an extension of multiness to high dimensional parameter spaces, very high dimensional parameter spaces, thousands of dimensions. I haven't really studied the paper, so I can't recommend it. I just want to say it exists as a tool in case you're interested. Good. So that's multiness, and that's one of the tools of choice that I and many others have been using in many different settings to do this kind of Bayesian model comparison. So let me conclude in the last 5 minutes or so by showing you some cosmological applications of this idea. Now I have a detailed example about inflation here, which sadly I won't have time to go through because of time. I'm happy to share the slides for those of you who are interested in the details. I just want to, what do I want to say? What I want to say is this, that we have this cosmic background data, and we discussed yesterday how they can be used to learn about the cosmological parameters that control the expansion of the universe, but actually there's another set of important cosmological parameters that parameterize the initial conditions. That's to say, the conditions that emerge from the end of inflation. Those parameters, where are we? Sorry, I'm just trying to find one slide to summarize what I want to say. Those parameters are can be related to the shape of the primordial power spectrum. That's the power spectrum that emerges from inflation. So this power spectrum can be parameterized in terms of its shape as a function of wave vector. And each one of those coefficients can in turn be related to the physics of inflation, more specifically to the shape of the inflationary potential during the inflationary phase of the universe. So there is a good deal of theory and numerical work that goes into making a relationship between these observable quantities, the shape of the power spectrum, with the shape of the potential that drove the scalar field that we think is responsible for inflation. I don't have time to go into the physics here, so I apologize for this 30-second summary of what is a very vast field. So, the point is that my collaborators, Jerome Martin, Christopher Engeval, and Vincent Benin, have done a great amount of work in this paper by summarizing over 70 slow-roll models of inflation, single-field inflation, and working out these encyclopedia inflationaries, working out essentially the predictions, the systematic predictions for all of those models. And those models are different models for what the inflationary potential should look like in the early universe. And they come with parameters, with free parameters that give you the shape of the potential. For example, one simple potential. There's a potential D of phi where the free parameters are the normalization of the potential and the power law index of this potential here. So that's a two parameters model. And you can make predictions for what the observable quantity should be from Planck under the parameters of this model. I won't go into details. What we have done together is to take then all of these models, which in the end we came up with 193 different models for inflation, and compare them systematically to each other using Bayesian model comparison. And here is one slide summary of what we've found. So this is the plot, the base factor for all of these models normalized to Higgs inflation, one of the models. And so models that are to the left of this line are models that are disfavored with respect to this of the fiducial model, that is Higgs inflation. And models that are to the right are models that are favored with respect to the Higgs inflation. So you can see that most of these models are disfavored very strongly. Some of the models down here are disfavored at very strong levels of evidence. This number here is -5 log factor, which means that all of those models can be thrown away with very strong evidence based on the Jeffrey scale. And so by doing systematic model comparison, we are able to focus, to zoom in on a bunch of models here that are either slightly favored, like this one here, or only very mildly disfavored with respect to this benchmark model, and throw away all the other models because they are strongly or moderately disfavored with respect to the Bayesian evidence. And so this allows us to gain theoretical insight on the kind of class of models that data prefer. So here is an example where we have classified those models by the kind of evidence that they have. You can see that all of the models, 26% of the models that are still viable in terms of Bayesian model comparison, are all of plateau inflation type. And this tells you something of the kind of inflationary potential that you're looking at and the class of models that the data prefer. And so then you can go on and look at the kind of models in this inflationary parameter space. I won't do it because of time. So this is a principal model comparison applied to cosmological model selection. Here's another example of that in this rather old review paper now. In 2008, what I've done, I've taken the baseline lambda CDM model, the one with 6 free parameters, and I've asked myself, what if we extended this parameter set by including new physics in different ways? For example, including initial conditions that are not adiabatic but are more complicated, which would be the hallmark of extra degrees of freedom and the inflationary potential. What if we change the shape of the primordial power spectrum in a more complicated way? What if we looked at non-flat universes or evolving dark energy or a more complicated organization history? And all of these numbers for the log of the base factor are mostly negative, as you can see, which is telling me that the baseline 6 parameters lambda CDM model is a fully sufficient description of the data at the time. So in a Bayesian sense, this remains the best model from a Bayesian perspective. And all of this extra addition of parameters and these more complicated models were not needed and are still not needed, even with the more complicated, the more precise Planck observation. Okay, so there is more I could say, but I have run out of time. And I am sorry that I'm not around in person to discuss it more with you informally over coffee. But, I hope this overview was useful. I just want to mention this very quickly because I've talked about Bayesian model averaging. I don't have time to go into the details. You can then take this one step further to obtain model-independent constraints that account for model uncertainty. In this example here, for example, I'm doing Bayesian model averaging for the curvature parameter of the universe. Here's the reference, the paper by myself, Joe Silk, and Joe's students, Miran Vardanian. And what happens is the slightly counterintuitive result of this model averaging in particular case is when you include the possibility of non-flat universes, constraints for the curvature parameter, an average over the uncertainty in the models. So you see here a concentration of probability that corresponds to flat models, and then tails here that corresponds to closed and open models. It turns out that the parameter constraint, because of this concentration of probability effect, become actually stronger than if you assume that if you don't do model averaging concentration. And so, for example, if you want to constrain the number of Hubble spheres in the universe, how many Hubble horizons fit into the into the observable universe, then you get that, into the curvature radius of the universe, you get a lower limit, a 99% credible level of 250 Hubble spheres, which is 8 times stronger than if you didn't do Bayesian model averaging. If you want to constrain the radius of curvature of the universe, you get a limit of 42 gigaparsecs, which is about 50% stronger than the limit that you would get without Bayesian model averaging. So by using model averaging, you can also leverage constraints in the parameter space, parameters that you're interested in. Okay, I got a slide here with references. I'll put it in the PDF that I'm going to share with you. There are some, there are some references for Bayesian model comparison. My review article, Brandon Kelly's work, Tom's paper, Giulio D'Agostini's good primer, Phil's book, of course, and so on and so forth. There's plenty of good stuff in here. On this, I think I have run out of time. Thank you very much for your attention. Again, apologies for not being there in person. I hope it was as good as it could be given the constraints, and I hope you've enjoyed it and you've learned something. Thank you very much. Thank you. My pleasure. Apologies again. Okay. Any questions, let me know by email. Bye-bye. Bye, guys.